we discussed the Weierstrass approximation theorem, so we proved it. So any continuous function can be approximated by a polynomial to arbitrary accuracy with respect to d infinity. And today I'm going to prove the generalization. I discussed one aspect of that at the end of last lecture. Even to state the Stone-Weierstrass theorem requires me to discuss some additional structure on this space, which we haven't discussed up till now, which is that it's not just a topological space, it's actually an algebra. Well, in particular, it's a topological group. And that's why that material was in the tutorial, for instance. So I know you've all, in principle, done group theory and linear algebra, so you've seen fields and so on. Did you discuss algebras over a field? No. Okay. So you've seen vector spaces. So let me define an algebra relative to that notion. So an algebra over a field, R, and all my algebras over R, is just a vector space. I'll say what the structure is in a moment, but I've sort of already talked about that in some context. So it's an R vector space equipped with a multiplication. So the multiplication is some map which takes a pair of elements of my algebra. Well, it's not an algebra till it's equipped with the multiplication, I guess. So it takes a pair of elements of my vector space and gives me another element, which is the product. And that product is the function whose definition is that it takes x to the value f of x, which is a real number, times the real number g of x. Okay, that's a function. I mean, we can check by hand that it's continuous, but the whole point of us thinking hard about function spaces is that we never have to ever do such boring checks. Okay, so how are we going to set up this structure in a way that we don't have to check anything? Well, so maybe, I want to argue that this multiplication is continuous. I also want to argue that all the structure in the vector space operations is continuous, right? So maybe I'll say it like this. So recall, so I'm still defining this algebra structure. Maybe I should finish the sentence. So an algebra, it's a vector space together with a multiplication defined, well, in this case by that, such that, okay, and an algebra needs to satisfy some rules, and I'll elaborate those in a second. But before I do that, let me spell out how I get that map and the other maps involved in the algebra structure on this particular space. Yeah. Okay, also I've written x instead of AB. This is, what I'm about to say is true for any x. All right, so the basic point is that addition, multiplication, which I'll write as a bullet when I'm writing it as a map, and I guess if you like negation, continuous, right? Well, we discussed addition and negation in the context of arguing that R was a topological group, and multiplication, well, we all believe that's continuous. Okay, so building off that, for any continuous x, I have the following operations. guess I'm going to need locally compact Hausdorff. Okay, so there's a product, and I can take the diagonal map So the diagonal map is just the continuous map from x to x cross x, which is given by doubling the input. Now, then I can feed that input into into the function which is a point of that space. That's the evaluation map. And if you like, I can rearrange the order of things just so that's more clear. Right, so that's just moving the second factor past the third. Right, so that's a homeomorphism. And then I can do the evaluation map on both of those factors. The evaluation map is continuous because x is locally compact Hausdorff, so that's continuous. That gets me to R cross R. And then I can compose at the end with, well, whichever one I like, let's say addition. Right, so that's a continuous, it's a composite of a bunch of continuous maps and therefore continuous. A continuous map. Now remember that given a continuous map out of a Cartesian product like this one, we can move one of the factors over. So just read, the reason I wrote that like the way I did, you should read that entire composite. That's a map from this triple product to R, and I can always get a continuous map by moving one of the components over to form CTS XR. And that's always continuous. Right, so I've constructed some continuous map like that, and if you see what it's doing, it's taking a pair, and what does it send it to? Well, it sends it to the function which, given an x, so read this composite in the following way. I've got little x f g, that gives me x x f g, that gives me x f x g, that gives me f of x g of x, that gives me f of x plus g of x. All right, so that's the map which assigns to a pair its sum, and by construction not only is that sum continuous, but the operation of producing the sum is a continuous map. Okay. Similarly, we get all right, so that function, that's what we call f plus g. That function is what we call f times g. Maybe I'll add in, so scalar multiplication, so that is in the same sort of way. You produce a map which takes a scalar and a function, say lambda and f, and gives you the function which takes an x and sends it to the scalar lambda times f of x. Right? So that function which takes x to lambda f of x is lambda f. That's also continuous. Okay, so these operations satisfy following laws. So let's call that map A for action of scalars. So that's product, that's plus. So as long as X is locally compact Hausdorff, that set with that operation and the action is an R vector space. Okay, that's easy to check. And well, what's the structure of an algebra? Well, it's that multiplication operation. And to say it's an algebra is to say it satisfies the following rules, namely that multiplication is associative, that there's an identity for multiplication, and the identity, well, given any real number I'm going to write, so given a real number lambda, I'm going to write also lambda for the function from x to r, which is just the constant function lambda. Okay. So this 1 here just means the constant function, which sends every element of x to 1. And then, well, it's clear that the multiplication works like that. The multiplication distributes over addition, well, on both sides, but this algebra is commutative, so I don't have to write the other side. Oh, I missed one, which is that scalar multiplication is bilinear. Okay, so the way to read this is take two functions f and g, continuous defined on x, real valued, multiply the first by lambda as I described, then multiply the result by g. That's the same as multiplying f and g and then multiplying by the scalar lambda and doing it to g before multiplication. Yeah?
What is A in this case?
Yeah, that was just this map here. Yeah, the name A is, I'm never going to use it again. It was just to connect these two boards.
Cool.
Yeah, so it was just this. Yeah. Okay. All right, so these axioms spell out, well, more precisely what a commutative algebra is. Okay. So for any locally compact Hausdorff X, CTS XR is a commutative R algebra. All right. Okay, so we say a subset. So throughout all these definitions, X is locally compact Hausdorff. So we say a subset is a subalgebra. If it contains all the constants, which is the same, given what I'm about to say, as saying that the constant function 1 is in there. Well, if you get two functions which are in the subset A, then their sum is in A, their product is in A, and any scalar multiple of anything in A is in A. So if lambda f is in A for all f, well, and 1 is in A, then lambda times 1, which is the constant function lambda, is also in A for any A. Sorry, for any lambda. So the constants are all in A. Okay, maybe I'll, so in particular. Now, as soon as X is non-empty, I can identify the subset of constant functions of that space with R itself, right? So, and the multiplication and addition of functions is then exactly matched by addition and multiplication in R, so you can identify R as a subalgebra of CTS XR via the constant functions, and that's contained in any subalgebra. All right. So this is all required to state the Stone-Weierstrass theorem. And why? Why do I care about subalgebras of this space of functions? Well, because that's what polynomials do. So the polynomial functions that I've written on that first board over there, that is a subalgebra of CTS ABR. Right? So I can do that more generally. As soon as I can sit my space inside Rn, I can talk about polynomial functions. I haven't introduced terminology for this before, but I've been using the concept. So an embedding between two topological spaces is a continuous bijection. Well, if I have any continuous map from x to y, and I take the image, that's j of x, then that j induces a continuous map from x to j of x. So if j is a bijection, that's also... Yeah, what am I talking about? That's a special case. An embedding is a continuous injective map which induces a homeomorphism. Yeah, okay. So its image, well, that's a bijection onto its image. That's not necessarily a homeomorphism, as we all know, right? Because the image of opens don't need to be open in the subspace topology. But if that's the case, that is, if it's a homeomorphism, then we call it an embedding. Sometimes I've been saying homeomorphism onto its image, so that's a synonym for embedding. Okay, so given an embedding, just think about x as a subspace of y. The reason I'm introducing this notion is that what I'm about to define, strictly speaking, depends on the choice of embedding, so I have to introduce this notion now. So given an embedding of, say, our space x into Rn for some n, well, I know what it means to say a polynomial function from Rn to R, and using the embedding, I can restrict, so to speak, any polynomial function on Rn to x, that is, I can precompose it with j, and that gives me a notion of polynomial function on x. Okay, so the polynomial functions on x with respect to the embedding j. I put the r there. Let's think of this as sitting inside CTS xr. So that is, well, as I said, all the restrictions of polynomial functions on Rn to x. So that is, it's f circle j, where f is polynomial. Okay. All right, so lemma. In that notation, that's a subalgebra. I mean, that's easy to check, right? Because polynomials are closed under addition, they're closed under multiplication. Constants are polynomial. So if you think about it, you'll see that that subset is always a polynomial subalgebra of I guess here well, I don't need to say that, do I? Because x is a subspace of well, anyway, let's say it. All right. Okay. So definition. So a subalgebra separates points well, this is again an attempt to, I mean, when you think of subalgebras of this space of functions, you should be thinking about polynomial functions, right? That's your model conceptually. Now, polynomial functions have a special property among And they're not a generic subalgebra. And that special property is that, well, let's think about it this way. So if I give you 2 points in Rn, which are different, well, then they differ in some coordinate. But the function which reads off the ith coordinate is a polynomial function, right? So to say that to distinguish points is exactly to find a coordinate which is different is precisely to say that the functions, the collection of functions which are all the projections, or like the coordinate functions, is to say that collection of functions separates points, which is to say that a collection of functions separates points is to say if you have 2 distinct points, there's some element of your collection of functions which takes a distinct value on those 2 points. Right. So that's a property that polynomials possess, and well, those aren't a subalgebra if I just take that set all on its own, right? Because the product of 2 coordinate functions is not a coordinate function, it's a polynomial function. But if I close this collection under the operations of addition and multiplication and scalar multiplication, I get exactly the set of polynomials. So if you like, the point of polynomials is that they contain the coordinate functions and they're a subalgebra. And to say that they contain the coordinate functions is essentially just to say that they separate points. So the virtue of the set of polynomials is that it's a subalgebra and it separates points in the following sense. So we would say a generic subalgebra separates points if for every pair x, y, and x with x not equal to y, there exists an f which is in your subalgebra which takes distinct values on those 2 points. Okay, so example. For the reason I just explained. Okay, so the argument that we're about to make is that it's this property, or 2 properties if you like, that polynomials are a subalgebra and that they separate points, which is responsible for this. Okay, for the fact that they're dense. And more precisely, as soon as I have a subalgebra which separates points and which is dense, and which is a subalgebra which separates points, the claim is that it's dense. That's the theorem. Well, provided X is compact. It's not true, it's only locally compact, incidentally. There's versions of it which are true, but you have to then talk about the compactification. If X is compact Hausdorff and A subalgebra which separates points, then A is dense. All right. So it's a pretty impressive claim. Let me state a corollary before we get into the proof, which is the generalization of the Weierstrass theorem beyond just intervals. Right, so that's an immediate consequence given the statements we've made so far. Take X to be a compact subspace of Rn. Then take, well, just the inclusion to be your J. Then this is just polynomial functions in the obvious sense on X. And that's a subalgebra which separates points by the argument I just explained. And therefore, by Stone-Weierstrass, it must be dense. Okay, so that generalizes that statement up there. Is there a question? Yeah.
Is that what you mean by dense?
Oh, yeah. So I just mean, I just mean this. So if I have a subset, so if, did I not define this in the lecture? So I apologize. So if X is a subspace, X is dense if the closure, that is the intersection of all closed sets containing X, is Y, which is to say that Y is the smallest closed subset which contains X. I mean, stated in terms of metric spaces, so if Y was a metric space, which is the case here, right? To say a subset is dense is to say that there's, given any element of Y, there's some, and an epsilon, there's some element of X within distance epsilon. Yeah. So if you think about this case with Weierstrass, that's the statement I've got written up there. So that distance, that condition, that given an F, there's an epsilon and a polynomial with d infinity distance less than epsilon is precisely the statement that the subset of polynomials is dense. Okay, so that's what we're aiming for. Okay. So I need, oh dear, well, if I do the proof of the lemma, I'm not going to be able to get through the theorem. So I'm just going to state this, I'm sorry. Given that we have no lecture next week, I want to get to the end of this part. So, I'll explain why you must believe it. I mean, it's not meant to be immediately obvious why that's the case. So if I take a subalgebra, and then I close it under all sort of limits, right? I take all points which are limits of elements of my subalgebra. I'm claiming that then the set of all limits is still closed under addition and multiplication. Okay, well, but I sort of explain the reason, right? Because multiplication doesn't just give you a continuous function if you feed in two continuous functions. It is a continuous function, right? So if you continuously vary f and g, the output varies continuously. Okay, so suppose I had a convergent sequence of elements of A. So I've got Fn, where Fn is in A. And I've got Gn, where Gn is in A. And I take the Fn's to some limit F and the Gn's to some limit G. Then the Fg's, well, Fg, which is the limit of the Fn Gn's. But Fn Gn is in the algebra because A is an algebra, so it's closed under multiplication. So that means that the image Fg of the limit points under the multiplication map is itself a limit of a sequence in the algebra. That is to say that it's in the closure of A. Okay, so that's the argument. I mean, the way it's spelled out in the notes is not done quite like that because I'm doing it more generally, not just for X compact, where I could use a metric. Okay, well, that's the reason why that's true. That's true because multiplication, addition, and scalar multiplication are continuous maps, and I explain why that's the case. All right. So here's the main trick, I would say. Okay, so at the end of last lecture, I defined the absolute value of a continuous function, just post-composed with the absolute value function. That's again continuous. I guess you probably saw this trick when you did real analysis, but the minimum of a pair of functions can be written in terms of the absolute values of the differences and the sum. Sorry, the differences, right? So the min is a half f plus g minus f minus g. That's a function, right? So if you feed in an x, so min fg, so f and g, two functions. Min fg is another function. It's the function whose value at x is the minimum of fx and gx. And if you just look at the right-hand side, you'll see that that's a correct formula for it. And so that's what that function is. And similarly, max, that's where I take the sum. Okay, so, well, that's a scalar multiple of a sum of functions, all of which are continuous, so that's continuous. Definition. Okay. So here's the lemma. So let X be compact. Now this is why I need compactness. Okay, well, we know how to produce closed subalgebras, right? Because, well, that's, by closed subalgebra, I just mean a subalgebra which is closed as a subspace. Because I can just take a subalgebra and take its closure, that's still an algebra and it's closed. So we're not worried about the presence of closed subalgebras, we know how to make those. And the claim is that if X is compact, and I take a pair of elements of a closed subalgebra, then the absolute value, the min and the max, are all still elements of my subalgebra. That is not obvious. Well, what's obvious is that, I mean, that's three claims, I guess, right? That is in A, that's in A, and that's in A. The second and third claim are obvious consequences of the first because of this, right? If I could show that the absolute value of anything in A was still in A, well, then f minus g is in A, because A is an algebra. Therefore, that part is in A, and therefore the rest of it is in A. Okay, so it's easy once I know the absolute value of anything is in A to show that the min and the max are in A. So that's all we have to show. But that's what I explained at the end of last lecture. Right? So I'll just sketch the argument. So what you do is fix an f. The image of X under F is a bounded subset, so it lies in some interval like that. Look at that bounded subset. The absolute value is a continuous function on that, and I know by Weierstrass that I can approximate it by a sequence of polynomials, call them Pn. Well, then that means that precomposing this sequence, all of them with F, and this guy with F, and using continuity of the composition, that sequence of functions, so this is a sequence of functions from X to R, right? Because F goes to this interval, and then Pn goes from that interval to R. So that's a sequence of functions in the space CTS XR, which converges to the absolute value. and these are all polynomials. Right? For the simple reason that, if I have the square function and then I compose it with any old function f, right? So that's x squared circle f. Well, that is the function which you could write as f squared, right? You evaluate it on a number, it evaluates f at that number and then feeds that number into the squaring function. So that's exactly what f squared is. So the composite of a polynomial function with f is a polynomial in the sense of this algebra in f. Well, polynomials in f are contained in A because A is a subalgebra. So that's an element of A. So what have I constructed? I've constructed a sequence in CTS-XR, all of which, the elements of which are in A, which converges to the absolute value of f. And A is closed, so the limit of any sequence in A has to be in A. So that shows you f is in A. Okay. All right. So let's prove the theorem. So that was the reason we did the Weierstrass theorem first, so that we knew we could approximate the absolute value by polynomials, and we needed that in order to show that the absolute value of f belongs to any closed subalgebra containing f. Okay. So first, let us perform a reduction. We can prove, it suffices to prove the theorem in the case where A is closed. Right? So if I'm given an algebra A which separates points, well, just replace A by its closure. That's still a subalgebra. It's closed. It still separates points because given a pair of points which are distinct, I could find an f in A which distinguish them, and, well, A is contained in the closure of A, so that still works. Okay, so I can assume that A is closed. So what are we going to do to prove that the closure, well, now we actually want to show that A is equal to CTS-XR, right? So we need to show A is equal to the whole thing. So to do that, given an epsilon, we need to produce a G which is in A. So we want to, given a pair, that is an F which is in CTS-XR, and an epsilon, we want to produce an approximant to F which is within this distance of F. So again, think of A as being polynomials, so this is a polynomial approximation to F in some sense. Right, so we need to build up an approximation to F somehow. Well, it's not clear how we're going to do that. All we know is that we've got an algebra and that it separates points. Okay, so we're going to have to use that in some tricky way, the fact that it separates points, to construct some ingredients out of which to build a G.
So that's an F in CTS-XR?
Yeah, that's right. Okay, so let me tell you the collection of functions out of which we're going to build the approximation. Okay, so for every pair of points in A, choose a H which separates them. We can do that by hypothesis. And then f sub st is going to be it's just the linear interpolation which has the following property, which is that fst at s is f of s, and fst at t is f of t. So what am I trying to do? I'm trying to build approximations of f, right? So, I mean, suppose that I'm working in the case where we already know it works, that is on an interval. So there's my f, say. There's s and there's t. Well, if I'm going to build an approximation of f, I can start with approximations to f near a pair of points, right? So I want my fst to look like f near these 2 points. So it should be continuous. The things I'm trying to construct, it should be continuous, it should be in A, that's the whole point, and it should be like f near both s and t. Okay, so let's verify this formula does the job. First of all, and that's just a number, so that's a constant function plus a scalar multiple of something which, given the way that algebras work, that's clearly in A, right? So that's okay. And if you just substitute s into it, if I wrote the formula correctly, you get f of s, and if you put t into it, you get f of t. Okay. All right, so let's say that's what our approximation looks like, roughly speaking. Okay, so to there, I think, anybody could come up with, but now it's sort of clever, right? Okay, so, well, as I've drawn in the picture, I mean, there's no guarantee that fst looks anything like f away from s and t, right, clearly. But we can figure out where it looks like f to the relevant degree of approximation, which is epsilon, right? That is, we can set ust to be, well, so it's take the function fst minus f. Forget about this for the moment. So that's continuous, the difference is continuous, the absolute value is continuous, so that's all a continuous function. And I can take the pre-image under that function of this open interval, which is the set of all x in x such that the absolute value of fstx minus f of x is less than epsilon, right? Which is to say f of fst, this element of A, approximates f to the relevant degree of accuracy on ust, which is open. Right? So that's some. I mean, notice that s and t both belong to ust, right, by this condition, because this number in here is 0 at s and t. Okay, so at least we know it's some open neighborhood in x of both s and t. All right. Now, the reason for setting up this min and max is because that's the ingredients out of which I'm going to, well, that's the operations rather, which I'm going to apply to this collection of functions in order to generate the approximation g. But it's a bit of a trick. Well, I mean, so what do I mean it's a trick? I mean, if you just tried to start with those ingredients, I mean, it's not so easy to see how to construct out of mins and maxes an approximation, right? Because you start taking mins, that's going to make sure it's not too big, but of course it could explode on the other side. right? Because if I took two of these approximations, say fst and fs prime t prime, and just took their min, well, where fst is good, fs prime t prime might be really bad, and I take the min of that, well, it's going to be really bad, right? So I have to think a little to use min and max to construct the approximation. And the way to do it is to fix one of the points. Okay, so I fix S, and I look at all the fst's as the t's are varying. Well, varying over points not equal to S. Okay, so that's some collection of approximations, but they all look good near S, right? Just like this fst does. They're varying wildly everywhere else, but they look good near S. And what I'm going to do is take the minimum over some finite number of those. And I know I can take finitely many because I use compactness of x. Okay, so find t1 up to tn such that x is equal to ust1, ustn. I mean, that I can do because with S fixed, varying the t's, well, t belongs to ust, so that is a collection of open sets which covers x, so it has a finite subcover because x is compact. Take some finite collection of ti's that makes it a subcover. And then I'm going to define, so S is fixed, and that cover depends on S, and from that I'm going to construct the minimum of the associated approximations for all of those ti's. So I just do this operation, well, what, n minus 1 times. And, well, if I feed in functions which are in A, as the fst's all are, then because A is a closed subalgebra, this lemma tells me that the result of all those minimums is still in A. Moreover, if I evaluate the minimum at S, well, because the S is the same in all these approximations, and each one of them has the value f of S at S, that's just f of S. Okay, so the h of S is still a good approximation to f near S, but maybe not everywhere, but at least it's bounded above. Maybe I'll explain. Okay, take a point in X, then it belongs to some USTJ. And by the construction, that's less than or equal to FSTJ at X. And, well, that is constructed. The whole point of USTJ is that if I take a point in it, then FSTJ is less than f of x plus epsilon. Right? That was the whole point of this open set. So that's less than fx plus epsilon. But that didn't depend on the j. That was for any x. Okay, so I've got this bound everywhere. Okay. Well, let's be more precise. So what is the open set on which this approximation looks good around S? It's the intersection of all those open sets. Well, S is in VS, so the sets V1, the sets VS, S in X, cover X. Choose a finite subcover, V1 up to Vm, say, S1 up to Sm. And then we're going to take G to be the max over Fs1, Hs1, Hsm. Okay, so the HS's were in A, so those are all in A, and that's a finite max, and maxes of things are in A, so that's in A. And I just need to convince you that it's got the correct property with respect to f. Right? Yeah.
What do you mean by in VS is where HS is a good approximation?
Yeah, I should spell that out. Yeah. Well, that'll come up now, actually. So yeah. Right. Because, well, this is where FST1 has an appropriate bound, right? But I'm taking the min over all of them. So if I want to bound HS from below, I better know that all of those are bounded from below. But I know the bound for each of them only on the appropriate USTJ. So I need to take the intersection of all of them to get the bound on HS. Yeah, so let me, I'll spell that out now. So first of all, note this. Well, why? Well, because all of the HS's are less than f plus epsilon. It's a finite max, isn't it? So if I take the max over all of them, that's going to be true. All right, so I just need to argue for this inequality. Okay, so evaluate it at a point x. So if I take x to be in x, say x is in V S I, then f of, so G VSI is by definition USI T1. These T's depend on the S, right? Oh, dear. Okay, so notice that, well, since x is in VSI, therefore x is in USITJ, and therefore, if I look at that inequality, it says on the other side that fx minus epsilon is strictly less than FSITJ of x. Well, therefore, taking the minimum over the j's, which is how I defined hs, right, it's less than that, but that's by definition hsi of x, and it didn't depend on the I either, so well, that's to say, then I took the max, right? So okay, so that gives us that this difference is less than epsilon for all x in x, which tells us the d infinity distance is less than epsilon. And so we're done. Okay, sorry for going over time, but I wanted to get through that before the break.